Welcome everyone, my name is Bogomil Kamiński and this is DataFrames.jl tutorial prepared for the Julia Academy. In this part of the tutorial we will present you how you can apply a split apply combine approach to data frames processing. This means the general strategy is used in order to quickly and easily aggregate data across different groups defined by some columns of a data frame. We will be using the files generated in the previous part of the tutorial. And first we load the packages that we will depend on. So first it's data frames, then CSV and arrow for reading and writing data frames to disk, statistics for statistical function, fractables to create cross tabulation, and pipe in order to improve the way how you can chain functions in Julia. So in the first step, we update the number of displayed lines and columns by the Jupyter notebook in order to make them a bit wider and a bit shorter, because this is a nicer way to display data frames in this case. And as you can see here, I'm reading in the auto2 CSV file using CSV file command. And what is important here, that CSV.jl package does auto detection of the format of the CSV file. So if the CSV file is well formatted, then actually I do not have to do anything to get a CSV file properly read in. This is as opposed to the previous part of the tutorial where we had to do some manual preprocessing of data in order to correctly read it in. And then I pass this file read in into a data frame constructor to get a data frame as a result. So here df is a data frame that we already know from the previous part of the tutorial. I could have equally well read in this data frame using the arrow.jl package from the arrow file that we have created in the last section, the last part of the tutorial similarly. The only difference, and we can see that those two data frames are identical. The only difference that is important to know is that arrow.jl, as opposed to CSV.jl, has a special type of vector that it creates. So it's not a standard vector, it's arrow primitive type. What is the reason for this? The reason for this is that arrow is super fast in reading in the data. It achieves it by memory mapping the file on disk. But the downside is that such a column is not mutable. So we have pros and cons of such an approach. We get speed at the cost of immutability. So what is the simple solution to convert columns of a data frame read in using arrow.jl into standard vectors? Well, it's simple. You just need to copy the original data frame read in using arrow.jl, and after copying it, the reference to the memory mapped file is lost because we have just done a copy of those columns. And now those columns, as you can see here, are just standard Julia vectors. So if you would like to see more information about how to work with arrow format in data frames, here you have a link where you can see the details. So let us first start with showing you how to group the data frame by some column. So this is easily achievable using a group by function, and as you can see here, I'm just using group by, pass a data frame and tell by what column or columns, as you will see later, I want to group by my data. So in this case, I'm grouping by my data frame by brand, and you can see that we get a grouped data frame which has 37 groups because we have 37 brands in our original data set. What is important when thinking about group data frame is that creation of a group data frame is essentially the same as if we have created an index for our data frame. So now the brand column is an index added to a data frame, and this index is very fast and can be easily used to look up groups of our data frame grouped by the index. So for example, if I wanted to extract as a part of our original data frame that is associated with the Ford value in the brand column, then I just pass a tuple that has a single value Ford, and I get, as you can see, only rows that have Ford as a brand. Why a tuple? Well, a tuple is needed because if I had more than one grouping column, then I would need to pass the values for all grouping columns as consecutive values in this tuple. But what is most important here, that since this is an index, this lookup is extremely fast. So this lookup is as fast as it would be a dictionary lookup. So we do not do linear filtering of our data frame. This lookup is done almost instantly because we only need to get a hash value of our key, which is quite useful and very often used when working with group data frames. Apart from using a key to group a data frame, we could also have used an integer index to the group of the data frame, and then Chevrolet would get index 1, and Nissan, because this is the last one, would have index 37. So we can get groups by value or by number in the group data frame. So as promised at the beginning of this tutorial, the point is not only to group by the data frame, which is often useful in itself, but actually to show you how you can process the whole data frame in groups. So the first function that we will use here is a combine function that in this example calculates the group-wise mean of NPG column. So you can see here the syntax I have already introduced earlier, where for any transformation, you first write the source column, and then after a per symbol, you write a transformation you want to apply to this column. So in this case, the source column is MPG, and I want to calculate the mean of this column. And as you can see here, we get as a result a grouping column because it is by default always preserved, and the result of our calculation. You can see here that Julia is smart enough, and in data frames we create a new column consisting of the name of the source column and the name of the transformation function. So we get NPG mean column name as a result. What if I didn't like this target column name? Well, it's easy enough to specify the target column name yourself. In this case, you have 3 elements in the chain of transformations: source column, then transformation, and finally target column name. So we can see that I'm transforming MPG using min function, and I want min MPG to be the name of the resulting column in our output data frame, and this is exactly what we get here. So for further analysis, because we have only 37 rows in all the columns that we process, I will increase here the number of lines outputted to 50 so that we can see all the 37 groups that are rows by 37 groups that were produced. So we have here created a brand MPG data frame, but this data frame is ordered by the order of groups that were created by group by. What if I wanted to order it by MPG min? Well, it's easy to do using a sort function. Here we see that it's sort bank, which means that it will be an in-place operation. And I'm sorting brand MPG by MPG min, and ref equals true means that this will be sorted in a descending order. So we now see that the brand that has highest MPG min is Volkswagen, and the brand with the lowest MPG is high. So let us move on to another typical data processing task. So looking at the original data frame here, we can see that we have those brands of cars and they can have different origins. We have an origin column, and it would be interesting to understand what this column is. So first, I am using a very powerful Fractable function from Fractables.jl package when I'm creating a frequency table of our data frame taking brand and origin columns. So you can see here that now in rows I have brands, and in columns I have the values of origin, which is 1, 2, 3. And what is interesting here is that you can see that I have retained in this array information about axis and about names of the axis. So this is a pretty nice way to present the results. And what is useful is that we can visually see, which makes sense, that each brand is assigned only to a single origin. So it most likely looks like origin 1 is North America, origin 2 seems to be Europe, and origin 3 seems to be Asia. So let us investigate it a bit more. So now we will create an analysis using split apply combine approach. And here I also introduce this, I use a pipe.jl package where I pipe several transformations. And as you can see here, I use underscore to denote where in the consecutive transformation I want to use the output of the previous transformation. So what I do here, I take a data frame, I group it by brand, and then for each group, I take the origin and calculate how many times, how many unique values of the origin are given in the data frame for this specified brand. And we can check here that as a result, I get ones everywhere, which means that indeed there is brand is associated with only one origin value. Maybe one thing to note here is that because I have not specified in combine here the name of the output column, And here we have used an anonymous function which didn't have a name. We see that the default name of the anonymous function is just function. So the column name is origin function. Let us check if indeed there is only value 1 in all of the columns, and it's easy to do using extrema, for example, and we see that the lowest and highest value in the origin function column is 1, which means that really there is a unique one-to-one mapping between, sorry, not one-to-one, but each brand is assigned to only one origin. We could have also grouped by our data frame by 2 columns, by origin and by brand, and then we could calculate how many times a given brand is present in a given origin. You can see here that, for example, in our original data frame, we have 43 entries of Chevrolet for origin 1. Now, note that passing n row is a very convenient way just to get a number of rows per group. So here I'm combining the group data frame and just saying, calculate me the number of rows per group. Having such a data frame, this is typically called a tall format. We can use an unstack function to convert it to a wide format where each origin is given as a separate column in our data frame. So I unstack this origin brand 2 by brand, means I keep brand as row identifiers, but put origin as columns. And n row, so number of rows, will be put as values in the unstacked data frame. Now you can see here that the order of the value is 1, 3, 2, and this is because this was the order of appearance of origin in our source data frame. So we can see that it was first 1, and the second value that was present was 3. So this order is retained here. Now, the only thing that is not so nice with this table is that it contains missing values. And in our Frac table, originally, we had zeros because there were no entries for those elements. So how to quickly switch missings to zeros in our data frame? Well, it is very easy to do using the coalesce function. When I'm broadcasting a coalesce function over all elements of origin versus brand data frame and replace missings by 0. So coalesce works exactly the same as in SQL, and it's very useful way to replace missing by some value. In this case, we replace it by 0. And now, except for the order of columns and rows, we have recreated the Frac table that was presented earlier. You can see here that the only difference is that in Frac table, by default, both rows and columns got sorted, while we didn't opt in for sorting here, but of course we could. Now, the last thing is that this example also shows you why it's useful to allow strings to be used to identify column names. In this case, we have those column names 1.0, 3.0, 2.0, which are not very easy to express as a symbol, but you can easily use a string to access a given column. As you can see here, I extracted column called 1.0. Finally, let us highlight that the power of a data frame in Julia is that it can store any object. So in particular, it can store vectors. So here what we do, we write a bit more advanced split applying combined transformation, where for each origin, I want to extract the brands that are associated with this origin without duplicates. That's why I'm using here unique. Now the question is, why have I used this ref here? So we can see first of all the result. So the result is that now I have a brand function is a vector of vectors. But it's best understood why ref is needed if you omit it. So if we omitted ref, you can see that DataFrames.jl would automatically spread the results into multiple rows, which is most commonly, this is what we would like to have, but sometimes you want to avoid spreading vectors into multiple rows, and you can easily protect them exactly like in broadcasting in Julia base by wrapping them in ref. So if you wrap something in ref, then it's retained as is. So in this case, we get a vector of vectors in origin underscore brand free data frame. Here I show that we can easily check whether indeed there is no intersection between origins in terms of brand names. So what I do here, I use intersect function from Julia base that takes two sets and calculates their intersection. In our case, those two sets are columns, rows I and J from brand function column of our data frame. And so I check 1 versus 2, 1 versus 3, 2 versus 3, so all combinations, and indeed again we see that we have no duplicates. Finally, the question might be, if I have data in this format, so a vector of vectors, how to flatten it? This is a pretty commonly needed operation, and for this you can use the flatten function, which exactly does what we have seen above. So takes a data frame where some column, brand function in our case, is the vector of vectors, and then spreads this vector into multiple rows. So applying flatten on this data frame gives me exactly the same data frame as we got here above with unique, but without using this ref. So all those options are quite powerful, and I have only scratched the surface of what functionality split applying combined strategy can give you in Julia data frames, but I can tell you that we have put a lot of effort into designing it to be fully flexible. And if you are interested in reading the details, please check out the Julia data frames manual that is available online, as it provides you with a full specification of what kinds of transformations are supported. So thank you very much, and I invite you to listen to the next part of the tutorial.